we're going live in 3, 2, 1. Hi, everybody, and welcome back to another one of our QGIS Open Day sessions for September the 24th, 2021. And I'm joined by Jakob Levalius. How did I do with your name pronunciation?
That's good.
And you're going to be showing us detection of ditches in QGIS using classification, if I'm not mistaken. And so over to you, Jakob. Thank you for joining us. And if anybody has any questions during the presentation, just use the live stream, the chat in the live stream, and I'll pass them on to you at the end, Jakob.
Okay, thanks.
Okay.
Let's see first if the screen sharing works. Can you see my screen?
Yes.
Good. So my name is Jakob Levalius. I'm coming to you from Sweden, southern Sweden. And it's good to be here. So let's talk about automatic ditch identification. Maybe not a common problem, but it's something I've been working on for a while. So who am I? I am a physical geographer, and of course I've used GIS a lot for about 20 years now. And I worked on a project called Vattenatlas for the past 6 years, and that is basically it's a service that is intended to erase the administrative borders. So if you're going to plan for water management, it's not good to, have data limited at administrative boundaries. So this service is pretty much just combining from just different municipalities all the data and using all the national data to have everything in one place. And the service is built on PostGIS, and I'm using QGIS and the QGIS server. So why do I need to identify ditches? Well, the elevation data I'm using is based on LIDAR, which I guess is pretty common these days. And this data doesn't consider culverts. So you need to modify the data to do accurate hydrological calculations. And if I can identify ditches, it would make it easier to find the culverts and to modify those. And in addition, the Vattenatlas that I've been working on is also intended to highlight ditches. So that's one of the reasons as well. Ditch is also known maybe as a trench or a channel or a dike, and dike is the Swedish word, so you'll see that throughout my presentation as well. And I was trying to find resources on how to do this online, but I couldn't find anything. And I don't know if this approach is novel or anything, but it works for me. So this is the service I built, and it's called Vattenatlas. So it's basically water atlas. And what I want you to look at in the screen is this is the runoff. And the intention is not just to show where the water flows, but also how it flows. So this is just one layer in this map, and it's showing if the water is running as ground runoff, or if it's running in a ditch, or if it's running in a culvert. And in addition to those three types, there's also a red line, and that is where the water diverts if culverts are saturated. So an extreme scenario, just assuming that the culverts are going to be not going to be available. So that's where the water would flow in an extreme scenario. So that's why it's important to me to identify the ditches and digitize those so I can present them in this map also. So before we go into the live demo, some characteristics about the ditch. It is, of course, a local low. So it will be pretty easy to identify these just using a neighborhood calculation and extracting the low points. But you would also get a lot of noise, and you would also get this type of scenario, which is the edge of a hill. If it's steep enough, it's going to appear as a local low. And you can, of course, adjust parameters so you can try to fine tune to get what you're looking for. But we're going to, even though we're not going to use this approach, we still need this layer in our calculations. So we're going to do this local low calculation. So it's a neighborhood calculation to calculate the average height. And I'm going to use a neighborhood size of, actually going to use 7 and not 5. It all depends on the data, of course. I have 2 meter grid size data, and if you have, so depending on the grid size, you go up or down in neighborhood size to get the local low. And then I just see which cells are lower than the average, and I can use an extra distance there to filter out some noise. And so I'm using 0.1 meters there. So let's go into QGIS, and this is the raster I'm using. It's just a small part of my actual data. And if you can, of course, visually see ditches in this data. It's pretty clear where ditches are. But as you zoom out, it's more difficult to see them. So another benefit is if you digitize them, you can zoom out to a larger scale and still see where they are. So the first thing we'll do is just do a local calculation here, local low. So we'll use the height, the digital elevation model. We're going to use 7 cells there. And just save this to a new folder here. Should go pretty fast. So the result here is going to be a byte, Boolean. So it's just showing what's considered a low point. And as you can see, it picks up all the ditches here, but also a lot of spurious points everywhere. And in other places, we can see the example of hillsides being a local low. So alongside, I have a hill here. Yeah, alongside this hillside here, there's a local low on the other side too. So we don't want those, but we do need this layer, the local low. So moving on, we're going to look at the slope of the data, and we're going to filter out anything that's below a certain degree. We're going to use 5 degrees for that. And also we're going to look at the aspect. So a ditch has, of course, 2 sides, and these aspects are going to be the opposite. So the difference in those is going to be 180 degrees, which is an important fact to this calculation. So we just start by, of course, creating the slope and extract everything above 5 degrees slope into a Boolean raster. And then we do the aspect calculation, and then we just multiply these. And I made a model for this. So we can, sorry. Aspect selection. So should go pretty fast. So this is showing us the aspect and excluding the cells that are less than 5 degrees. So moving further then to how we're going to use the aspect. We have, as I mentioned, the difference in these two are going to be 180 degrees. So we're going to use that in a neighborhood calculation. So if we have a neighborhood size that encompasses the ditch and the size of the ditch, when we run that neighborhood calculation, what you see here in the top view is supposed to be the cells, the raster cells. So let's say that one cell is the slope on one side, and that has an aspect, and the one in the middle, the aspect really doesn't matter in that one. But we have two different aspects. So when we calculate the neighborhood value for the cell in the middle, the minimum is going to be one of the cells on one side, and the maximum is going to be one of the cells on the other side. So doing that, we're going to get a layer with a minimum aspect and a layer with a maximum aspect. And the cells in the middle of the ditch are going to have both of these. So we can use that as we go along. So we do a neighborhood calculation for the maximum aspect, and then a neighborhood calculation for the minimum value. And of course, depending on the size, the grid size, we want to use different neighborhood sizes because we want to make sure we get the whole ditch. If we have a big stream and we want to include that, we might go to 10, to 7 or 9, or I'll get to that later. And then we just calculate the difference between the maximum and the minimum, and that should get us the difference. So the difference we're looking for is about 180 degrees, and that means we have a ditch if the difference in these is about 180 degrees. But that's not the whole truth, and I'll get to that. But let's do the calculation. So we're going to use, let's do the three, let me just highlight this so it's selected. We're going to use a neighborhood size of 3. I'm going to call that 3. So we can try to visualize this layer. And look at the values closest to 180. We're going to go from 100 to, let's say, 260 for now, and clip the values outside the range. So just have a visual of the data. And what you can see here is it's picking up the ditches that are in the data. If you compare it to the local low, that includes a lot more of the data of the terrain. But one thing that is also included in this about 180 difference in degrees is anything that's elevated. So the top of a mountainside, or just a stone wall or something, some kind of perimeter could be elevated. So we need to take that out as well. But we're getting a pretty good visual of the ditches and the data. So moving on to the next step, to eliminate the elevator features, which of course also have this same characteristics of these two slopes that are 180 degrees apart, aspects, sorry. So we're gonna, what we did with the symbology, we're gonna create a layer that's classified as either dike or elevated. And so we're doing that here. Dike or elevated. So now it's just black points again. And then when we have those, we're going to use the one we created from the beginning, which is the local low. So if we multiply our dikes with the local low, we will get the ditches. And at the same, the opposite, you can also, if you're interested in the elevated features, you just calculate a local high and use that. So the local low, which one is it? This one. So we just call this the dike. So now we have pretty close to what we're looking for. We have identified dikes, and it's not complete. And to make it better, we can use another neighborhood size and then add those two together. And I'm going to show you the result of that. That's going to pick up a lot more of the data. I'm going to show you that later, but once we have this, we can create a polylines from this using two operations. Let's see here. Yeah, again, this multiple neighborhood sizes. I've used 3 and 5 and just put those two together. I'll show you that later. And if you go really big, you might have to adjust your local low neighborhood size as well. But to vectorize it, we first have to thin the lines so they're not too many cells wide. So we do these two calculations, R thin and then R to vect, to get the polylines. So I'll show you that here. First, to thin the lines. So they are slightly thinner, and then the final calculation is to vectorize these lines. You might need to visualize this better. So I hope you can see the result here, and it's pretty good. It's not, the idea from the start was, can this be done completely automatically so I don't have to do anything manually? And I haven't quite reached there yet. So so you still, if you want to digitize, you can still use these and use them for snapping and stuff. But there are gaps. Some gaps can be filled by extending lines. There's operations for that. But then that can create some problems where they start to cross other lines that aren't supposed to be crossed and stuff. My tips would be to try to find neighborhood sizes to find the appropriate ones for your data and location. So I have the 2 meter data, so I'm using 3 and 5 mostly because I'm not interested in the bigger streams. And of course, as you saw, I'm using models for just, it's quickly, and I can fine tune the data. And I have another example here, is when I have the this one here is using 3 and 5, and you can perhaps see that it's more complete, even more complete. And so many ditches are pretty much uninterrupted, so it's a pretty good result. And yeah, so this has been valuable to me, and it's what I use to create the data for Vattenatlas.
Jakob, did you? There was a question about the model. Maybe could you show us, just for visual eye candy, what the model looks like that you created?
Which one of them? There were many.
And there was another question: could you share the models? Or is that long list all of them? I mean,
yeah, I can share them. I don't know how, but yeah.
There's a model sharing platform on plugins.qgis.org that I can show you offline from the call, if you like. Okay. So could you explain, is that whole list used to produce the result, or?
Well, I used about 5. I had different, some models are just variations on others, but I have a lot of models that are later stages of running the hydrology calculations. So I have a lot more models than a lot of models for that. So.
And do you have one sort of meta model that wraps up the whole process then?
Well, I tried to. I find that if I put too many calculations in one model, I can get an error that's difficult to locate. So, yeah.
And another question is, when you get this result, so the next step is somebody goes and digitizes and closes the gaps between the streams. Did you look at using imagery and maybe seeing if there's extra information you can get from an image classification rather than terrain classification?
I use images for optical, it helps me
information.
It helps me in some cases to find, to figure out what's happening. But I haven't used classification on images. That's difficult when it comes to ditches and in woody terrain. You're just going to see trees. So many of these ditches, or most of them actually, are in wooded areas. So.
Right. Okay, well, thank you very much for showing us that. And maybe just one last question. So the process you've shown, you've done it in a small area. How did you do it across all of Sweden, or are you just doing it for a specific municipality or something? Or
well, it's southern. When I'm extending the total size of this area that's been mapped, and when I'm finished, it's going to encompass this most southern region of Skåne, which is 11,000 square kilometers.
Okay.
So that's that's going to be the total area I've mapped.
And do you have to process it in pieces and combine them, or is it?
Yeah, I do one catchment at a time. So there are about, I guess, 10 or so major catchment areas.
Well, that's very wonderful to see what you've done. If somebody wants to get in contact with you, could you share? Okay, there you've got it.
Yeah, yeah, I'm on LinkedIn, and also if you check out that service Vattenatlas, you can find me through that as well. And I have an interest for those. There might be someone listening who knows SQL pretty good, and I'm looking for someone who knows SQL who likes historical mapping. So, just a shout out.
What will the sales pitch for them be? You want to help capture historical maps, or?
Yeah, I'm trying to create something, and I'm looking for some SQL expertise.
Great. Well, Jakob, thank you so much for your for sharing what your work and your your time with everybody, and hopefully in the future your models as well. And hope we'll see you again in an open day soon.
Yeah, well, thanks for having me. It's been fun. So thanks.
Great. Okay, thanks so much. Okay, I'm going to stop the stream, and then we can catch up about the sharing afterwards if you want to. Oh, thanks, Jakob. I think